In this lesson, we'll talk about the limit of a function. And for the most part, this intuitive definition will be good enough for what we do in this class. So here's the idea. You have a function, and you have some point a. We say the limit of f of x as x approaches a equals some number L if we can make the values of f of x arbitrarily close to L by choosing values of x close to but not equal to a. And in this case, we'll write this symbol. The limit as x approaches a of f of x is equal to L. This can also be written as LIM for limit, and then next to it you can write x approaches a of your function f of x is equal to L. So same thing. To explain what this definition is saying, let's look at example 1. Here we have a piecewise function f of x, which is defined as x plus 1 if x is not equal to 3, and 2 if x is equal to 3. We will use this function to determine parts a, b, c, and d. I want to start actually by graphing this piecewise function, and I'll put it right here. So for the most part, as long as you're not equal to 3, your function is the line x plus 1. That is, it has slope 1 and a y-intercept of 1. So it's pretty easy to sketch. You can plot the y-intercept. The slope is 1, meaning that it goes up 1 and over 1. So your line looks like this. So here is the line x plus 1, and this function is always equal to this line except at 3. So the way we'll draw this is we'll go up to 3, and we're going to skip over it at this spot. So we'll put an open circle and then keep going at that point after. So except at 3, the function always equals the blue line. But then at 3, we define it to be the number 2, so I'll put a closed circle here. And here's a graph of the piecewise function f of x. Let's look at part A. We're asked to compute f of 1, and this is not a limit. What this is asking is, if you're at 1, what does the function equal? What's its y value? And I can see from the graph it's equal to 2. You can also look to the definition over here and say, well, not 1 falls into this category, meaning I'm using x plus 1 as my function, and 1 plus 1 is also 2. No matter how you do it, this is equal to 2. Great. For part B, now this is a little different. It says, what is the limit as x approaches 1 of f of x? So here we're asking, all right, as the values of x get close to 1 but not equal to 1, what is happening to the y values? So for example, if you looked at 0.9 or 0.99 or 0.999, what are those numbers approaching? I'm going to write a table of values for this to try to figure this out. So here's my table. X versus f of x. In the table, technically according to this definition, you're not allowed to use the number 1. You can only use numbers that get really close to 1. So you could say, well, try 0.9. The function at 0.9 is up here. I'll put 0.9 in place of x, and I get 1.9. Okay. You can get as close to 1 as you want, so you could do 0.99. And if you put 0.99 into the function, you'll add 1 to it, so you get 1.99. And you could, go one more time, 999. Same thing's going to happen. You get 1.999. And you can also approach 1 from the other side. You could say, well, maybe I could use 1.01. And if you do, you're using this part of the definition, and you get 2.01. At this point, I have a good idea of what the limit is equal to. It looks like these numbers are getting closer and closer to 2. In fact, that is the answer. This limit is 2. And if you take a step back, it almost looks like this definition is somewhat, pointless. I mean, the function at 1 is equal to 2, and it's actually the same thing as the limit. But that makes sense. As you get closer to 1 on either side, the y values are always going closer to 2. So it turns out that f of 1 and the limit as we approach 1 are the same. This begs the question, well, what is the point of this very lengthy definition? I think parts C and D will help explain that a little bit better. Let's start with f of 3. Again, this is not a limit. This is asking, what is the y value of this function if you put 3 in place of x? Well, here's 3, and the value you get is 2. So looking directly at the graph, you also get 2. And you can actually use this equation as well. When x is 3, we're defining it to be 2, and that's why this is the answer. But what is the limit as x approaches 3? Will it be the same thing as the answer for part C? Let's again use a table to try to figure this out. So I'll draw a table down here. It'll be x versus f of x. And the point of a limit is to never use the number 3. You can use numbers that get closer and closer to it, but you just can't use 3 itself. So for example, you could say, well, I could use 2.9. If you put 2.9 into this function for x, you're not using this part, you're using this part. And if you put 2.9 here and add 1 to it, you get 3.9. Okay? You can get closer to 3, so you could say, well, 2.99. Again, if you go to this function, you're not allowed to use this part. You can only use this one. If you add 1 to it, you get 3.99. And maybe just one more, you could say, well, even closer would be 2.999, and this is 3.999. You can also go on the other side of 3. You could say, well, what about 3.01? Again, you're using this part of the definition, meaning you're adding 1 to this, and you get 4.01. What are all these numbers getting closer to? And the answer is these get closer and closer, it appears to be 4. Notice that this is different than f of 3. This is the purpose of this definition. It's to analyze what is happening around a number instead of using the number itself. Sometimes the answers will be the same, but really what we care about here for a limit is when they are not. So the answer to this is actually not 2. The answer is 4. If you then go back to the graph to examine it, so here's 3. If you don't use the number 3 itself, the numbers on the function are always getting closer to 4. And then on this side, again, they're always getting closer to 4, where this hole is located. The only time that you can get this value is if you use the number 3 exactly. But the point of this definition is to never use that number. Let's try this idea again in example 2, where we're going to find the limit of a piecewise function. This one is called the Heaviside function, and we're going to denote it h of x. First, I want to actually graph this piecewise function and then use the graph to figure out these two things. All right, so this one as a piecewise function has 2 parts. If you are strictly less than 0, and then if you are equal to 0 and greater than it. If we are strictly less than 0, the function is itself equal to 0. So the way we'll draw that is like this. It's a horizontal line at 0. And then when you get to 0, I'll put an open circle here, meaning it's 0 as we get closer and closer to x is equal to 0, but it'll have a missing spot right there because there's no equal sign on the inequality. Now, if we're equal to 0, but greater than it, the y value is always 1. Meaning I'll put a closed circle here and a horizontal line going in this direction. Maybe I'll include some arrows to indicate that this goes on forever in both directions. Okay, part A is, what is the value of this function at x is equal to 0? Again, this is not a limit. According to this formula, this is where equals 0 occurs, and the value is 1. So h of 0 is 1. And you can see that on the graph too. At x is 0, it isn't 0, but it does equal 1. Now the second question involves a limit. This one says, what is the limit as x approaches 0 of this function? Let's try to use, again, a table of values to figure this out. So, all right. I'm going to have x versus h of x. And the idea with the limit is you're not allowed to use 0 itself. You have to use numbers that are getting close to 0, either from the left or the right. I'll start with this side. Numbers that get close to 0 would be things like negative 0.1, negative 0.01, maybe negative 0.001. These are all getting closer and closer to 0, but they never equal 0. The values that we get for h are, according to this formula, 0. It doesn't matter what number you put into the formula, it always returns 0 back. So this is 0, this is 0, and this is 0. From this, it looks like, oh, well, the limit itself must be 0 because these numbers never change. But we can also check this side too as we approach 0, but with positive numbers. So we could check, well, how about 0.1 or 0.01 or 0.001? These are all getting closer to 0, but only from the right. This time, we're using this portion of the definition, and we always get 1. So this is 1, this is 1, and this is 1. So something odd is happening here. If you look only at the left side of 0, it looks like the limit is 0. So I'll draw an arrow and say, well, from these three, it looks like we're approaching 0. However, from these three, it looks like we're approaching 1. So what is it? What is the answer to this limit? And the answer is, it does not exist, which I'll denote with a D and E. So if we use the symbol D and E, that's our way of saying does not exist. Let's more carefully define what's going on here, just to illustrate when a limit will not exist. What I want to define is a left-hand limit and a right-hand limit. So we'll say a left-hand limit and also a right-hand limit. When we say the term left-hand minute, it means we're approaching, but only from one side. So you're only considering one side. And left means from the negative side. We're going to use this notation here. You'll still use LIM, and x will approach a number, but we'll put a negative after it to indicate that we're only considering one side of this limit. Now, in this problem, the left-hand limit itself actually does exist. If you're only using numbers that are to the left of 0, they're always equal to 0, and therefore we can say there's just one number, and it's 0. For a right-hand limit, same idea. We'll write LIM as x approaches 0, but then we'll put a plus sign to indicate that we are only considering things from the positive side of the given number. In this case, we're only looking at this part of the table, and it looks like the answer is always 1. So in fact, this right-hand limit, 8 for h of x, does exist and is 1. So this limit does not exist overall because from the left and from the right, we're getting two different numbers. Let's state this as a fact that holds true for all functions that you work with. And that is, if the limit from the left of a given number of a function is not equal to the limit from the right of a given number, then you know the limit overall does not exist. So that's true. You could also state this fact as if the limit as x approaches some number of a function exists and let's say is equal to L, then it must be true that the limit from the left and the right are equal to that number as well. So you know the limit from the left of that function is equal to the limit from the right of that function, and they're all equal to whatever that number happens to be. In example 2, we saw a case where a limit does not exist, and that's when the limit from the left does not equal the limit from the right. In example 3, we'll see another case where a limit does not exist. I have the function g of x, and it's a rational function, and I've graphed it here. I want to figure out what these limits are equal to. Let's start with this one. What is the limit as x approaches -1 from the left of the function g of x? What this is saying is you look at -1 and you only consider this side of the function. We want to see what is happening to the y values of the function g. As we get close to -1 from the left, the graph is moving up, it's moving up, it's moving up, it's moving up, and actually it looks like it never stops. It stops only because it's outside of the window. But actually, this thing keeps moving up forever, and that's because there is a vertical asymptote at x is equal to -1, which I'll indicate with this dashed line. So this is a vertical asymptote. And that is at x is equal to -1. So this graph continues to go up forever, and it never stops. So you can actually say that this limit, well, it doesn't exist, but more specifically, it's equal to positive infinity, or simply just infinity. All right, what is the limit as we approach -1, but from the right side? So here we're looking at the y values of the function. Again, there's a vertical asymptote here, and that means the function goes up forever as well. And so this limit is also positive infinity. And we are determining this just by looking at the graph itself. Now, overall, what is the limit as we approach -1? Since both sides are positive infinity, we can simply say, well, this is positive infinity too. So in these three examples, we had an infinite limit. It is equally valid to say that these limits do not exist. If you have a limit that becomes infinite, it is true that they do not exist because they don't equal some real number. But you can write this in these cases just to be a little bit more specific about what is happening on your graph. So yeah, these don't exist, but more specifically, they are, in this case, infinite. Now let's look at parts D, E, and F. Here we're approaching 3 from the left, from the right, and then all together. As we approach 3 from the left side, we're looking at this part of the function. And again, it looks like we have another vertical asymptote. And this one occurs at, in this case, positive 3. So I'm going to note that there is a vertical asymptote at -1 and x is equal to 3. What this means is the graph is also going up to positive infinity. There is no other work to show, so down here I'll say, just by using the graph, this is my answer. Now, what happens as we approach 3 from the right? Now this time, the graph is going down, but this case that means to negative infinity. So it still is infinite, but it is a negative infinity. Overall, what can you say about the limit at 3? Here we have two different types of ways they don't exist. One's going to positive infinity, one's going to negative infinity. So really the only thing you can say here is that this limit does not exist. We were able to be more specific about how these limits didn't exist because it was only going to one thing on each side, but overall, the limit just doesn't take on any one value. One other thought about this example: if you look at the function, the numbers -1 and positive 3 create division by 0, which causes a problem in the graph. Sometimes when this happens, there will be a vertical asymptote. Another way of saying this is, if you pick a number and you have that the limit is infinite or it's going to negative infinity, if any of these things happen, there has to be a vertical asymptote on your function. I will state this as a fact on the next slide. So when is the line x equals a vertical asymptote to some function? This happens when any of these limits are infinite. If you approach that number from the left or the right or all together and they go to negative infinity or positive infinity, we will say that that is a vertical asymptote and that will appear on the function. Now, nothing about this definition will tell you how to choose what the number x equals a is equal to, but I'm going to note something here. If you're trying to find the vertical asymptote of some function y is equal to f of x, a good place to start is to check where the denominator is equal to 0. Potentially, that could be a vertical asymptote. It isn't always, but sometimes it is. In example 4, I have a function f and a function g. I want to use this idea to try to find vertical asymptotes of a given function. Let's start with this one in part A. F of x is equal to x plus 5 over x plus 4. Are there any vertical asymptotes on this function? A good place to start is by asking, well, where's the denominator equal to 0? And I know that number is x is equal to -4. And I'll abbreviate vertical asymptote as VA, but the question is x equal to -4 a vertical asymptote? The way we could check this is by seeing if any of these limits go to infinity in this function, any of them. I guess I'll go with maybe from the right. So I'll choose one of these here. And if I get positive or negative infinity, I know we have a vertical asymptote. So let's see. I'll set up a table. So this is going to be x versus f of x. And if I'm approaching -4 from the right, I'll use things like -3.9, -3.99, -3.999, and we could go on, but I think this will probably be good enough. I'm going to enter this function into my calculator. I'll just be careful with parentheses. And in the table, I'll plug in these numbers into this function. If they become closer to positive or negative infinity, I'll know we have a vertical asymptote. So let's see. For -3.9, I get 11. For -3.99, I get 101, grouped by like a factor of 10. And then I get 1001 approximately. And again, that grew by another factor of 10. I mean, these are getting bigger and bigger and bigger. So what is the limit as x approaches -4 from the right of this function? It appears to be positive infinity. We could have checked it from the left. We could have checked it all together, and potentially it may not have existed. But if you check it from the left, you're going to get some type of infinite limit too. But anyway, this is enough to answer the question that, well, because this limit is approaching positive infinity, the answer to this problem is yes. There is a vertical asymptote. It's at -4 for this function, and there are no others because there's no other place where the denominator is equal to 0. Let's try this again in part B, where g of x is equal to sine of x over x. We're going to be using radians here, so make sure your calculator is set to radians mode. There's only one number to consider where the denominator is equal to 0, and that is x is equal to 0 itself. So the question is x equaling 0 a vertical asymptote? Again, I could use any one of these limits. Maybe this time I'll try approaching 0 from the left to see if we get either negative or positive infinity. So I'll set up a table of values. It's going to be x versus g of x. And since we're approaching from the left, I'm going to use -0.1, -0.01, -0.001. Those should all be good. In my calculator, for this first one, it says 0.99833. 0.99833. That's probably rounded. Yeah, it goes on a little further than that when I scroll up to it, but that's good enough for our table. For -0.01, I get 0.99998. So 0.99998. And then for the next one, so it just rounded it in mine. So I actually scrolled over to it. More accurately, it's 0.9999998. So this really is 0.9999998. There's a 3 after it, but this is a very good approximation for it. Is this going to positive or negative infinity? Definitely not. Over here, these grew by a factor of 10. These are growing slightly, and in fact, they all look like they're going closer and closer to 1. In fact, that's what this limit is equal to. I'll write the limit as x approaches 0 from the left of sine of x divided by x. It appears to be 1 if we look at our table. Well, maybe from the right. Maybe from the right side it approaches infinity. So just because it wasn't infinite on one side doesn't mean, well, it could be infinite on the other. So we have more work to do. So we'll try maybe 0.1, 0.01, and 0.001. We can try those numbers to see what we get. So I'll go to my table, I'll type in these values and see what we have. So 0.1, 0.01, and 0.001. And I actually get the same values that I did for these 3 spots here. That is, at positive 0.1, it was 0.99833, then it was 0.99998, and then it was 0.9999998. These are approaching 1 as well. So it looks like the limit as we approach 0 from the right of sine of x divided by x is also 1. So I looked at the limit from the left. It wasn't infinite. I looked at the limit from the right, and it wasn't infinite. Is the limit overall going to be infinite? And the answer is no. I mean, because these two limits are equal, it means the limit overall exists and equals 1. So what does this mean? Is there a vertical asymptote at x is equal to 0? And the answer is no. So here's the deal. If you have a function and the denominator is 0, that could be a vertical asymptote, but you just have to check. One of these limits has to be true. If your denominator is 0, you have to find a place where one of these is true. None of them were true. Therefore, this is not a vertical asymptote. It actually turns out if the denominator is 0 and the numerator is not, you'll have a vertical asymptote. Over here, if you put 0 into the top and the bottom, you actually get 0 divided by 0, and there was no vertical asymptote. It's the fact that non-0 over 0 is a vertical asymptote. If you have 0 over 0, it could be a vertical asymptote, but sometimes it isn't. So to summarize in the previous example, if you have a function that's written as a fraction, and the top is not 0 and the bottom is, that is, if g of a is 0 and f of a is not, there is a vertical asymptote in the function. Therefore, you don't have to use the limits to try to justify your answer. If the top and bottom are both 0, possibly there's a vertical asymptote, but maybe not. It really depends, and you'll have to investigate further. Let's try this in example 5. I want to find all of the vertical asymptotes of this function. And the way we'll do it is not by using limits. What we're going to do is try to figure out, are there numbers that make the denominator 0 and the numerator is not 0? What we can do is actually copy down the denominator, which is 2x squared minus x minus 10, and we can set this equal to 0. Every number that makes this equation true could potentially be a vertical asymptote. To solve this equation, it's a quadratic. You could use the quadratic formula, but I think we could factor this thing. If we try to factor this, you have to have a 2x and an x. Next, I need two numbers that multiply to negative 10. And I gotta be careful here. I can't look for ones that multiply to negative 10 and add to negative 1, and that's only because we have this 2 here, which throws off that balance. I think if we put a negative 2 here and a positive 5 here, I think that will do it. Let's see. So I said a negative 2 and a positive 5. We definitely get a 2x times x, which is a 2x squared, and a 5 times a negative 2, which is negative 10. The middle terms are positive 5x and negative 4x. That adds to positive 1. Okay, I'll go back and edit my guess. That wasn't very good. I'll say, well, this thing really here should have been a negative, and this should be a positive. Now it should work out. I have a negative 5x, a positive 4x. That will give me negative 1. All right. So I'm going to check to see where each of these factors is 0. And this one is where 2x is equal to 5. So 5 halves. That could potentially be a vertical asymptote. And this other one is at negative 2. These two numbers make the denominator 0. If the numerator is not 0 for these two numbers, these are both vertical asymptotes. All right, let's see. If you plug these into the top, so my numerator is x squared plus 4. Well, this thing's always positive, but just to be explicit here, if you look at 5 halves squared plus 4, if you want a number for it, that's 25 fourths plus 4. And 4 is 16 over 4. So 25 and 16 is 41. So you get 41 over 4, and that's not 0. So basically what this means is this, x equals 5 halves, is a vertical asymptote of this function. What about negative 2? Okay, so for negative 2, if we put that into the numerator, that's negative 2 squared plus 4. This computation will be easier. That's 4 plus 4, which is 8, which is not 0. What does this mean? This means that both x equals 5/2 and x equals -2 are vertical asymptotes. So this and this, these are both vertical asymptotes. They make this fact true. I want to throw a what if into this problem. What if I changed that positive to a negative and left everything else alone? Would both of these still be vertical asymptotes for this function? This time the numerator can actually be factored. This function is the same thing as, well, the denominator isn't different, so I know it's 2x minus 5 times x plus 2. But the numerator is a difference of squares, meaning you can factor it as follows. It is x minus 2 times x plus 2. So x times x is x squared, -2 times +2 is -4, and the middle terms cancel. So here in this problem, if you use 5/2, it'll make this factor 0. I'll leave it to you to check, but the numerator is not 0. And for this reason, x equals 5/2 is a vertical asymptote. So is it a vertical asymptote? And the answer is yes. And the reason is the denominator is 0, but the numerator, this thing, is not. In fact, there's only two numbers that make the numerator 0, +2 and -2. So is x equal to, in this case, -2 a vertical asymptote? And the answer is no. One thing to notice here is that you can actually cancel these two factors, and the function is almost identical to just x minus 2 over 2x minus 5. I'll leave it to you to check by graphing the function, but if you put this thing into your calculator, you will not see a vertical asymptote at -2. And the reason is it does make the denominator 0, but it makes the numerator 0 as well, and those two factors can be canceled. So this function is almost identical to this one. This one doesn't have a vertical asymptote at -2, and neither does this. In example 6, I want to sketch a graph of this function below. It's a piecewise function, but it has 3 separate parts. I want to find all of the places, the numbers a, where the limit as we approach it does not exist for this function. Let's first draw a graph. So just a really basic sketch of what this function looks like. It is doing different things when we're less than -2, when we're between -2 and 1, and then when we are greater than 1. I'm going to mark these places on the x-axis. So here's -2, and then here's +1. The only numbers that I think we'll have to check where the limit exists or not is at -2 and +1, because that's where changes in the functions will occur. And potentially the limit from the left might not be equal to the limit from the right. When we are less than -2, the function is -2x minus 11. If you actually put -2 in place of this x, let's see, we get -2 times -2 is +4, minus 11 is -7. So let's see, we have -1, 2, 3, 4, 5, 6, 7. So at -2, that part of the function is approaching -7. I'll put an open circle because it doesn't equal it at that value, but that's where it is approaching. The slope of this linear function is -2. That means if we go back 1, we have to go up 2, which would be to -5. So I can put, some spot right here to get an idea of what this line looks like. It looks something like this. Again, this is a very rough sketch. But when we're less than -2, the graph is -2x minus 11, and it's heading towards this open circle here. Okay, next, between -2 and including -2 and up to and not including 1, the function is x cubed plus 1. So again, like at 1, you'd have 1 cubed plus 1, which is 2. So I'll put 1, 2. The function approaches that, but it's not equal to it. Now at -2, if you put -2 in place of x, -2 cubed is -8, and plus 1 is actually -7. So that fills in this spot here. it's a cubic function, which means it looks like this. But here is that middle portion. This was linear. It went down to -7. This one actually picks up at -7 exactly. It looks like x cubed plus 1, and it stops here. And then if we're equal to 1 and greater than it, the function is 3, which is a horizontal line. So that's up here. I'll put a closed circle and then this horizontal line. Again, a rough sketch, but the graph nonetheless. So where does the limit not exist? There's only really two numbers to consider, -2 and 1. Here at -2, does the limit from the left equal the limit from the right? And the answer is, yeah. I'm going to write this down as a fact. The limit as x approaches -2 from the left of this function is equal to -7. That's also equal to the limit as x approaches -2 from the right of this function. And this means the limit as x approaches -2 overall is equal to -7. And so it exists. Now, what about the other number? That was at -2. Well, what about at +1? Here, the limit from the left is not going to be equal to the limit from the right. The limit as x approaches 1 from the left of this function is equal to, let's see, the y values get closer and closer to 2. The limit as x approaches 1 from the right of this function is always 3. Those two are different, so these are not equal. And what this means is overall, the limit as x approaches 1 does not exist. So the answer to this question is, what are the numbers, the values of a, where the limit doesn't exist? There's precisely 1, and that is at x is equal to 1. I'll just note up here that they're asking for values of a, so a equals 1 only.